Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 8, 2025. So, just yesterday. It shows that some popular LLM re-ranking methods can require a staggering 9,900 model calls for a single query. The paper is titled, Efficiency Effectiveness Re-ranking Flops for LLM-based Rerankers, and it really challenges the idea that just using bigger models is always better for these kinds of tasks. To analyze this paper proposes a new hardware-independent way to measure computational cost, revealing that many popular methods are surprisingly inefficient. So to create this hardware-independent measure, the authors first had to figure out a way to count the actual work a model does. This table lays out their formulas for estimating flops, which stands for floating point operations, essentially a direct measure of the raw calculations involved. It provides these formulas for key parts of the model, like the attention mechanism. This lets them compare different architectures, such as multi-head attention and grouped query attention, on a level playing field, and it's the foundation for all the efficiency results that follow. This table then details the main results, comparing different re-ranking methods. We see a few key columns here. First is NDCG, or Normalized Discounted Cumulative Gain, which is a standard way to measure how good a ranked list is. Then we have the new efficiency metrics, RPP, or Ranking Performance per Petaflop, and QPP, Queries per Petaflop. These tell you how much ranking quality, or how many queries you get for a fixed amount of computation. The results are really stark. The pointwise methods, which score documents individually, are by far the most efficient. In contrast, the pairwise method, the one that got a high NDCG, required 9,900 model calls, leading to almost zero efficiency. Now, all of those efficiency numbers we just saw, they hinge on one thing: whether the author's method for estimating computational cost is actually accurate. And that's exactly what these plots demonstrate. They're a validation check. On the horizontal axis is the real measured flops, and on the vertical, the estimated flops from their formulas. The plots show results for both decoder-only models, which are great at generating text, and encoder-decoder models. You can see the data points form a nearly perfect straight line, showing a strong linear trend. This confirms their estimator is highly accurate. Building on that validation, these next plots connect the flops count to something more tangible: time. On the horizontal axis is latency, which is just the processing time in milliseconds, and on the vertical is the flops count. The charts show results for two different kinds of models, a QN decoder and a FLAN T5 encoder-decoder, and in both cases, you can see a strong positive trend. As the flops increase, so does the time. This is a crucial link, showing that flops are a great proxy for real-world latency. So, we've seen that more computation means more time. But what exactly drives that computation? These plots look at a key factor: input length. They show flops versus input length for a QN7B model and a FLAN T5XL model, and the trend is exactly what you'd expect: a straight line going up. The longer the input, the more work the model has to do. The charts also show both the real measured flops and the estimated ones. And again, the estimates track the real values very closely, reinforcing the validity of their whole approach. So bringing this all together, the big takeaway is that while LLMs are great at re-ranking search results, they're incredibly expensive to run. The authors introduce a clear, hardware-independent way to measure that cost. And their key finding is that simpler, pointwise methods, which score documents one by one, offer the best bang for your buck. More complex methods and just scaling up models give you tiny gains in quality for a massive increase in computational cost. It's a crucial reminder that for practical AI, efficiency is just as important as effectiveness. That's all the time we have for this week's AI Research Roundup. Thanks for tuning in.